All right, everybody, we got to do some reactions. Now, most of these are going to be reactions for alkynes. There's going to be a radical reaction that we're going to have to deal with here in a second. But I do want to point out before we get going with these reactions that this definitely was corrected in yours, because, of course, we would never, never, ever want to show an alkyne with anything other than linear geometry. So that certainly was corrected on your structure with my 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Oops, got an extra carbon. 5 carbon alkyne there. Okay, so I'm going to go ahead and point that out. I'm going to make that a little bit better in my drawing. So 1, 2, 3, 4, 5. And that's the drawing that I want to go with. This, of course, was replaced with that. So, all right, now let's get started with the reactions. Now, again, for the most part, these reactions are from alkynes. And the thing about alkynes is that they're very similar to the reactions of alkenes. So if you know those reactions, then you're going to have a much easier time understanding what's going on with these reactions. It's not like having to learn a whole brand new set of reactions because they are so similar. Let's take the first one, for example. It's acid with an alkyne, and it's an acid, it's H2SO4. We have a reaction that uses H2SO4 with an alkene. It does Markovnikov addition of alcohols. Now, you're essentially getting the same thing that's going to happen here. You're going to get a Markovnikov addition of an alcohol, and it's going to form an enol. Now, what we don't spend a lot of time talking about right at this moment with reactions is that the enol will tautomerize to a ketone. And so it is essentially the same reaction, but the product's a little different because of this tautomerization that's happening. Okay, what's going on with H2 and Lindlar's catalyst? Well, H2 would generally have you completely reduce the alkyne to an alkane, but Lindlar's catalyst is a poisoned catalyst. It stops the reduction at the alkene, and so that's what your product is going to be there. Now, what about this guy? I'm starting with something that has 4 carbons here. I've got 4 carbons there. I've added a bromine to an alkane. You should know that there's only one reaction that we know that works with alkanes, and that's radical bromination. So something like Br2 in the presence of UV light, so H nu. Okay, here's some good old ozonolysis, and ozonolysis is very similar with alkynes as it is with alkanes. We're still going to be breaking this bond, and that carbon and that carbon are going to go away from each other. Instead of forming a double bond carbon like we would in an alkene reaction, we're going to continue to oxidize that carbon all the way to a carboxylic acid. Now, the only exception to that rule is that if there's only one carbon, we don't form a carboxylic acid. In this case, we're going to form CO2. But in every other case, we would form a carboxylic acid with the other side of the triple bond as well. Okay, so we've got some excess Br2, and we're going to react that with an alkyne. And so we're just going to keep adding Br2 until we get tired. So we can add Br2 until we have the alkene with Br2 on it, and then we can add Br2 again. And so what we end up with is Br2 as much as we can. So it's just going to add twice. All right. Excess HCl. Okay, so with HCl in the first step, you would get Markovnikov addition of the HCl, and it would form chlorine at that final position. But since it's in excess, we're just going to do it again. And so you do get two chlorines attached at this Markovnikov position. So it is just like an reaction with an alkene in the sense that the regioselective outcome involves having two chlorines at the more substituted location, but with the additional pi bond, the reaction just continues to happen. It happens again. Okay, so here's a reaction. It's a reduction of an alkene, or excuse me, it's a reduction of an alkyne to an alkene. But the thing that we need to think about is what's going on with the stereochemistry here. This is a trans alkene. And so in order to get a reduction that stops at an alkene, we need to have a poison catalyst. And so there's two choices. There's Lindlar's catalyst and there's the dissolving metal reaction. Now, Lindlar's catalyst produces cis alkenes, and the dissolving metal reaction produces our trans alkene. And so we want to use the dissolving metal reaction for this one. Okay, now here we are. The thing about alkynes is that they are nope, forgot my extra carbon there. Again, that's fixed in your worksheet, so it should look like this. 1, 2, 3, 4, 5. It should be 6 carbons. And so again, the thing about alkynes is that this is the first opportunity that you really have to start making some carbon-carbon bonds. And that's a really interesting thing to do from a synthesis perspective. Okay, we're going to make some carbon-carbon bonds. And so how do we do that? Well, the general reaction involves an alkynide ion reacting with a alkyl halide in an SN2 reaction where the alkynide ion gets connected to the R group. And so here's our alkyl halide. We already have it established as a propyl group. So it's 3 carbons long, 1, 2, 3, and it gets connected to an alkynide ion. And so what we need to do is show the alkynide ion and have some sort of counter ion to go with it. And that's the preactant that made this reaction happen. Okay.